Under this bolted cover lies one of Earth's most ambitious projects, a hole barely wide enough to squeeze your head into. This is the deepest hole ever dug on Earth, the Kola Super Deep Borehole, a 12-kilometer deep hole in the ground that took 2 decades to drill and in the process unearthed some unexpected scientific discoveries. Drilling this deep into the Earth is not done often, and for good reason. We simply do not have the technologies to do it quickly, but the treasures that lay below the surface have encouraged engineering startups to find a new way to drill even further. And if they succeed, it could help humans transition to renewable technologies without building new power plants. One company, Getty Images, is looking to adapt a technology developed for nuclear fusion reactors to solve the challenge of digging holes this deep. They make some big claims, so I wanted to visit their facility in Houston, Texas, to see the technology in action for myself. So, what are those treasures? Deep within the Earth, fission reactions generate immense quantities of heat. The Earth's core is 6,000 degrees Celsius, and just 0.1% of the planet's heat content could supply all of our energy needs for 2 million years. However, accessing that heat is not easy. Some countries like Iceland have it lucky with that geothermal energy reaching close to the surface, so close that geysers of boiling water erupt from the ground. Areas like this are rare, which is why geothermal energy accounts for a tiny fraction of the world's energy supply. We have a safe fission reactor under our feet, but we simply can't access it easily. The deeper you go, the hotter it gets, with temperatures increasing roughly 30 degrees per kilometer, and the hotter the temperature, the more energy we can extract, especially if we can create supercritical steam. Steam turns supercritical when it reaches a temperature of roughly 374 degrees Celsius and a pressure of 22 megapascals. Supercritical steam has some special characteristics that make it highly efficient at driving a steam turbine. The problem is, reaching the depths where supercritical steam can be created is basically impossible in most locations with current drilling techniques, because the cost of drilling increases exponentially with depth. Once a geothermal power plant is up and running, its operating costs are very low. But the issue is the capital cost of creating the plant. Most of the cost, around 50%, comes from the drilling process, and that's for relatively shallow drilling depths. To create a geothermal power well, you need to drill at least 2 boreholes. Drilling the 2 holes necessary for geothermal wells to a distance of 3 kilometers would cost around $6 million. But doubling that borehole depth to 6 kilometers would cost $27 million. Here's why. The extreme conditions as you drill deeper makes operations extremely hostile to machinery. The heat damages drill bits, and the rocks become tougher to drill through too. So, progress begins to slow, and drill bits begin to break more frequently. And replacing the drill bits gets harder the deeper you drill too. To replace a drill bit located at the very bottom of a kilometers deep borehole with stacks of drill pipe above it requires the entire stack to be pulled up. The longer the stack, the longer it takes. With drilling engineers being highly skilled and in-demand professionals, their time isn't cheap. The hole also becomes more unstable as you drill deeper. Boreholes also need reinforcement with steel pipes and concrete, which also becomes more difficult and costly at deeper depths. If the borehole does collapse, the entire drill stack could be trapped and require a new hole to be drilled. But what if we could drill without even touching the rock face, and use that higher heat to our advantage? This is what Getty Images is trying to do, by using extremely high power, high frequency electromagnetic waves to vaporize the rock. And they want to do this using something called a gyrotron, which sounds like a made-up word, but they are commercially available devices that are a critical technology in many fusion reactors, where they are used to heat the fusion plasma to the absolutely insane temperatures needed to achieve fusion within the reactor's magnetic containment. It works by generating a beam of electrons within a vacuum. The electrons are accelerated and pass through an extremely powerful magnetic field. Here the electrons begin rotating around magnetic field lines, and with the correct magnetic strength, this rotation can reach a resonance mode that allows the electrons to emit vast quantities of electromagnetic radiation. It works on similar principles to lasers, but instead of producing visible light, it produces higher frequency microwaves, giving it the name maser. This can then be piped out of the gyrotron through waveguides and directed where it's needed. The plan here is to drill using conventional methods until the conditions make progress too slow and expensive. For this reason, a good portion of Quase's focus is on integrating this technology into existing drilling equipment, so existing skill sets and existing technologies can be used. The drill stack will simply be replaced with the waveguides, which are essentially just hollow metal pipes. The high power millimeter waves are transported to the rock face with the waveguide, where it first melts and then vaporizes the rock. A nitrogen purge gas is continually fed down the tube to extract the vaporized rock. But with careful control of some parameters, we can just melt some of the rock, which can help form a casing of melted obsidian-like material, something we saw in Quase's bin of test articles. This all sounds extremely sci-fi and a little far-fetched, so I wanted to get a look at the drilling process firsthand. This is real-time footage. Keep in mind here that the rock is being vaporized. The once solid rock is being converted into a gas. This vaporized rock is then blown away by the purge gas. The test room this took place in was covered in strands of what looked like glass fiber. These fibers were being formed by the vaporized rock, and I am very glad I was wearing a mask while in that room. To vaporize rock in this manner requires an incredible amount of energy being directed into a small area, and I wanted to get a look at the machine responsible, hidden inside this shipping container. Here, I asked what the difference was between their gyrotron and those used in the fusion industry.
The difference between the gyrotron that's used in the fusion industry and our industry is really we're using the gyrotron as a source of heat. We really want to maximize that, and we really don't need the precise band that it's actually operating in. Whereas fusion is very precise to hit the tokamak, to hit the plasma. We basically have a little bit looser requirements, and so it allows us to have more flexibility on the design of the gyrotron for our future applications.
And with scaling this up to dig wider holes, that was the main reason you wanted the wider hole?
Yeah, that's right. We want to be able to go deeper and bigger holes in this regard. That's why you need to go to the higher gyrotron power.
Do you think the 1 megawatt version is as wide as for?
Yeah, so to put it in perspective, we're using a 100 kilowatts gyrotron to make a 4-inch hole, and at a decent, what we call rate of penetration. We actually are going 10 times more in terms of power now with the 1 megawatt gyrotron, but only doubling the diameter in this regard. So 4 times the area by going from 4-inch to 8-inch. But we're using 10 times more power. So we think we have enough margin there to make a larger hole with a 1 megawatt gyrotron.
Okay. And how quickly do you actually bore the holes based on your test articles so far? Like how long do you expect to be drawing 1 megawatt of power for these, these holes?
For the reference, so this one here is making a 4-inch hole in about 1 meter an hour. We want to be able to make an equivalent rate of penetration, 1 meter an hour for an 8.5-inch hole. In that
okay.
We don't need to be super
1 megawatt hour per meter, basically?
Yeah, that's right. So we don't need to aim to go extremely fast. We're going to work on that. But the reality is this is something that nobody can do with even current technology. So even going 1 meter an hour is already much faster than current technology. Because by the time you consider the actual regular drill bit drilling and wearing down and then pulling out of the hole, replacing that bit several days, then going back in, you add all that time up, your actual effective ROP is really much even slower than what we could do constantly or consistently, because we actually don't have a need to replace any parts. We basically are continuously drilling. So our effective ROP is actually pretty fast compared to conventional, where you actually have to trip in and out to
What does that acronym mean?
Rate of penetration.
Okay.
So this is how we gauge how efficient your operation is, your rate of penetration. How fast are you actually drilling? And because drilling time is money spent on the rig and personnel in that regard. So you want to minimize, or you want to maximize that drilling time. so that you can minimize the cost, the operational cost at the rig in that regard.
Is that your main limiting factor right now, just like the rate of penetration of?
Yeah, I think that's, we want to maximize that. Is the main requirements for us, is to maximize that. We don't want to spend, you know, more than several hundred, we don't want to spend hundreds of days drilling. We want to spend about 100 days of drilling these type of wells. So we don't want to spend years drilling this well. It doesn't become economical.
Right.
So it's all about how to make it more economical from a drilling point of view.
This was eye-opening to the challenges facing quays. 1 megawatt hour of electricity costs anywhere between $50 to $100. Quays wants to achieve a rate of penetration of 1 meter per hour with a 1 megawatt gyrotron making an 8-inch hole. At that rate, it would take 41 days of constant drilling and 1,000 megawatt hours to create a 1 kilometer hole. At a price of, let's say, $75 per megawatt hour, to drill a 1 kilometer hole would cost $75,000 in electricity alone. This actually sounds pretty reasonable, but again, this is their stated goal, not what they are currently doing. But the technology clearly works. A gyrotron absolutely can drill at a reasonable rate. The real question is whether it can do it in real-world conditions at a reasonable cost. Up to the date of filming, quays hadn't started field trials and were largely focusing on figuring out the science of drilling using this technique. In the lab, they've been varying different parameters, testing different rocks, different purge gas rates, and different distances of the waveguide from the rock face. The lab is absolutely littered with these test samples.
So what you see here is a variety of different samples that we've tested, and it's really testing out the recipe to make a very good hole and make a very long hole. And you can see there's a bunch of different shapes of it, and you can see some that are just glassy looking, and then some of them are bigger holes than the other. This is us playing with the different parameters of, do we send the microwave as what we call CW, meaning just full on, or do we pulse it? Or do we send pulse gas in different ways, high volume, low volume? Do we stand off from the launcher to the rock at a certain distance? So this is all playing with different parameters, and you're getting different results from it. So this is just a graveyard of different rock types and also different parameters that we're testing. So we have now a recipe that we plan to take to the field, and you know, that stack of rock there is the evidence, and those 2 rocks that you guys saw there are the evidence or the final recipe that we've come up with to take it to the field to make this 4-inch hole.
Does that change with the type of rock that you're drilling into as well?
It tweaks a little bit. What we found is basalt actually is a very homogeneous and actually will allow us to drill faster. But it's the same, we have now a recipe where we can actually have the same standoff, same amount of gas. And the benefit of rock that is a little bit softer, like basalt, allows us to go faster. Okay. Whereas granite has a little bit more quartz in it, so you have to spend a little bit more time melting it and getting it ready to be able to extract out the hole.
Is that just driven by like the melting point of the rock
Surprisingly,
itself?
Basalt and granite had very similar melting point, which is about 1200 to 1500 degrees C. But it's the granite that has a lot more quartz in it. And you can see the quartz in the white minerals inside there. That has a much different, it has more reflectivity, and it also has more, it has a higher hardness, and that requires a little bit more heat to be able to, more microwave to be able to get that to the melting point, to the vaporization point. So that's driving a lower ROP than it is something that is more homogeneous. Even though this is granite, it's more homogeneous than what we call the pink sunset type of rock that has very big chunks of quartz in it, whereas this is very uniform quartz inside here, and basalt doesn't even have that, and that makes it easier to even drill it into. So yes, the recipe or the type of rock will dictate how fast we go, but we think we have a recipe that's very insensitive to the parameters. It's just a matter of then being able to drill faster depending on the type of rock you're into.
Learning that higher quartz content affects drilling rates because it reflects the millimeter waves is pretty fascinating. And there are likely a whole lot more unforeseen circumstances in the real world that will raise the energy and drilling time for these boreholes. Water will be this technology's worst enemy. If water keeps infiltrating the hole, it would draw a huge portion of the gyrotron's energy as it boils. Some methods of dealing with this have been suggested. One method proposed is to feed material to the drill site that could be melted with the gyrotron, and this molten material would then flow and fill entry points for the water in the rock. But this itself sounds like it would be very time-consuming and imprecise. These are the types of things laboratory testing just can't give us answers to. Quaise needs to start drilling in the field, and that's exactly what they plan to do this year in Marble Falls, Texas. Getting to that point is an achievement in itself. Technologies like this frequently never leave the lab, and for good reason. Making high-tech equipment like this operate reliably in harsh construction site conditions is a challenge. Equipment needs to be containerized to be transportable, it needs to be rugged to resist the stress of transportation on rough roads, and a gyrotron needs a high-voltage power supply. Their gyrotron needs 50,000 volts DC, which the grid cannot provide, with the plugs in your home providing just 120 volts, and even industrial supplies being just 480 volts. So, Quaise had to have this transportable, temperature-controlled, high-voltage power supply custom-built in Switzerland. And they also needed transportable nitrogen generators and pressurized containers to provide the purge gas. They also need to containerize their gyrotron and protect it from the elements, and incorporate it into a conventional drilling rig. This is just one of those things with growing a startup. A proof of concept can cost millions to develop. A commercial 1 megawatt gyrotron alone costs $1 million. But getting that proof of concept out into the field and working outside of perfect lab conditions is another challenge altogether. Thankfully, Quaise has a good amount of funding, raising $91 million over 5 rounds since 2020. But it's time for them to prove this can work in the real world. Quaise began their first outdoor drilling tests this month, and there's plenty left to prove. It's clear that this technology is capable of drilling, but that doesn't matter if it requires an ungodly amount of gigawatt hours of energy to operate. There is one very simple metric an energy company needs to optimize for. For a source of electricity to succeed, it needs to outcompete other sources of electricity on cost. Its price per kilowatt has to be cheaper. We can estimate that with something called the levelized cost of electricity. The levelized cost of electricity is found by adding the initial capital costs and the total lifespan operating costs, and then dividing that by the total energy generated. Onshore wind energy is currently the cheapest form of electricity, coming in at a price as low as 3 cents a kilowatt hour, or $30 a megawatt hour. Quaise actually have an interactive levelized cost of electricity map on their website, which gives an estimate based on how deep they need to drill by location. In Marble Falls, where they are drilling now, the cost is estimated around $115 per megawatt hour, which is about in line with nuclear fission. But the cost of electricity is the main reason nuclear power is falling out of favor right now. But in other locations, it can get as low as $68 per megawatt hour, which is starting to sound more competitive. But these are Quaise's own numbers. Their final product could easily end up costing more. As with all geothermal plants, nearly all costs arise from initial capital investment costs. A gyrotron itself costs about $1 million. For a 7-kilometer deep borehole, they expect the waveguides to cost $2.3 million, the rig structure to cost $8 million, compressors and pumps to cool and remove vaporized rock to cost $7.5 million, bringing the initial capital cost of the equipment alone to $19 million. To drill a 7-kilometer deep borehole, the electricity costs, under the ideal conditions that Henry shared earlier, would cost $525,000 in electricity costs for the gyrotron alone. We aren't going to know if this number is realistic until they start drilling. Likewise, much of Quaise's vision depends on that obsidian-like casing working to reinforce holes and reduce the risk of borehole collapse. But that's something that can only be proved in field testing. But if Quaise can reduce the cost of drilling geothermal wells, they could trigger a radical acceleration of our transition away from fossil fuels, especially when we can adapt former fossil fuel power plants by drilling down for a new source of heat, drilling directly next to the power plant and bringing supercritical steam from the bowels of the earth to keep the turbines running. That is a compelling vision if the technology works. And it sounds like we will have some answers to that in the very near future. Companies like this depend on computer-aided design software. I learned at least 4 different design programs while working at different companies. All of them were insanely expensive and difficult to manage. This is what the founders of Onshape wanted to fix, to make engineering design software more accessible. Whether you are designing parts, creating manufacturing drawings, or performing finite element analysis, Onshape can handle it all, and it's available to try for free with the link in the description. If you are a hobbyist that wants to create models for 3D printing, this is a great option. However, they also have paid enterprise versions that you can also try for free. And because Onshape is browser-based, you don't need a crazy powerful computer even when running simulations. And it has other huge advantages. For example, engineers and designers are able to work together in Onshape at the same time on the same design from across the world, ensuring there's always a single source for your designs, a problem I had to contend with in my job as a design engineer, where sales reps kept sending out old, outdated files to clients. Onshape also has a plan available for government agencies and contractors who have to comply with government regulations like ITAR and EAR. So, Lockheed, if you are watching this, please tell Onshape that I sent you. Whether your company wants to evaluate a more modern CAD system, or you just need a CAD system for home projects, you can sign up for a free version of Onshape by going to onshape.pro/real engineering, or by clicking the link in the description or on screen right now.